Now we're going to put our theoretical algorithm to the test and run it on a real computer. So we present experimental results. So the experimental setup is, for the software, we use a program, BSP Sort, which is part of my library BSP EduPack version 2.0, which is the software connected to my book, and you can freely download it from my website with supplementary material for the book. The hardware is a single node of the supercomputer Cartesius, which is a supercomputer at SURF Computing Center in Amsterdam. It has 32 cores, this single node that we use. So the BSP library that we use, which is a communication library, is called Multicore BSP for C. And this way we can view the computer as a shared memory computer, but still in BSP terms. Then the test problem that we take is we just have an array of a certain size, like 1,000,000 or 1,000,000,000, and it contains random numbers between 0 and 1. The results that we get, on the first row you see the results of the sequential program, and the time, each time we multiply the length of the array by 10, and you see that the time needed grows a little bit more than 10, which fits with the n log n behavior that was predicted. For example, from 10 to the power 7 to 10 to the power 8, we move from 1.7 seconds to 19.5 seconds. On the other rows of the table, you see the time for parallel execution of my BSP sort program. On the first parallel row, you have the parallel program run on one processor. You see it takes slightly more time. For example, in the last column, at 20.8 instead of 19.5 seconds. That's parallel overhead that we have. But then it goes nicely down, and the largest array of 1,000,000,000 elements could be processed in less than a second on 32 processors. So we can define the speedup of a parallel program as the time of the parallel program compared to the sequential program. We divide the time of the sequential by the parallel program, and this tells you how much you speed up the execution. Note that we take the sequential time as a reference time and not the time of the parallel program with one processor, because that would be far too flattering. There could be a difference due to overhead. In this case, you see the parallel speedup plotted for P between 1 and 32 processors, and you see that we get almost a 20-fold speedup for 32 processors for the largest problem size. In general, you would expect here that the larger n, the larger the speedup that you can achieve, because the communication then becomes a little bit less important compared to the computation. We can expect speedup to be anywhere between 0 and p. On p processors, in general, you cannot expect to get a speedup of more than p. On the other hand, speedups are not guaranteed. There can be a slowdown, so a speedup over half is possible. If you have a very bad program, then that may happen. On the other hand, superlinear speedup, with speedup larger than p, can happen if you're lucky, and that is often due to the cache of the computer, the quick memory that is small in size. It may happen that if you have more processors, every processor has a cache, then altogether you get more cache memory. And then if the certain length n that you have fits into that memory, then suddenly all the computations you have go at a faster speed. The rate is determined by the rate for in-cache computations. So then you get superlinear speedup. The efficiency of an algorithm is also used as a measure of how well your algorithm performs. it is just a speed up compared to p. So it's sp divided by p. And generally, you would expect this to be a number between 0 and 1. And ideally, the efficiency would be 1. So a question to you. If we have 10 processors, and the sequential time is 5 seconds, the parallel time is 1 second, what are the speed up and efficiency? Well, you probably didn't have to think too much about this. The speed up is just 5 because we reduced the time from 5 to 1 second. And the efficiency is, well, we have 10 processors, so we could have achieved a speed up of 10. 5 divided by 10 is just 0.5, efficiency of 50%. Sometimes it's impossible to compare the time of a problem on one processor with the time on more processors, because the problem wouldn't fit memory-wise into a single processor. What you can do then is let the amount of memory and the problem size grow with the number of processors. For a distributed memory, computer memory grows. And so we are going to check how the efficiency is when the problem size grows. This is called weak scalability, in contrast to the strong scalability that we just talked about. That's why we keep a fixed problem size. So here we have a breakdown of the time of the algorithm of all the supersteps that we have. And the breakdown is based on a prediction, because we have our theoretical analysis. We measured the time that it takes on this particular computer, for example, to perform a flop. The flop rate is 5.7 gigaflop per second. We measured G, for 455, and L, it's a little bit above 100,000. So with these numbers, you can plug them into the theoretical formulas, and you get numbers which either predict very well, or sometimes they mispredict. But at least they give you some insight into the performance of the algorithm. And what you see here is the first 3 columns, they give the time for the computations. They are all kinds of sorting. And there you see that the predictions do not fit very well with the actual measurements. The bottom line is the actual measurement on the computer. And the reason is that the benchmark rate R is measured for efficient vector operations. It's called a DAXP. And we perform here not so efficient integer comparisons. So the R is not very reliable in this case for this particular sorting application. If we want to predict better, we would need to benchmark sorting and then predict. On the other hand, the other values for G and L, they give some insight. They tell you that yeah, most of the time is really spent in communicating the data. The 0.2 seconds is communicating the data. Synchronization is not very important, so that's also a lesson we learned from this. And altogether, the total time is in the last column. It's 0.5 seconds is the prediction, and it's about 1 second is what actually happens. So some of the errors in prediction, they cancel out, so that's lucky. The misprediction, this is what I just said, is due to the scalar operations that are not very efficient in the algorithm. To summarize, we've learned a few metrics for presenting the quality of an algorithm. So the speedup, SP, of a problem size n is the sequential time divided by the parallel time for p processors. The efficiency is this number divided by p, and usually we have speedup between 0 and p, efficiency between 0 and 1. Ideally, we would like to have the upper bounds, the speedup p and the efficiency 1. Now a question to you. Can you predict the time of a sorting algorithm for a BSP computer which has 512 processors, a computing rate of 6 gigaflop per second, a G equal to 1,000, an L equal to 4 million? These are parameters that are pretty close to the parameters of Cartesius with 512 processors and running the BSP on MPI library. You can use the most simplified approximation, n log n divided by p plus 2n divided by p times g plus 5l for the BSP cost of the algorithm. And we would like then to know what is the runtime in seconds and the speedup of sorting an array of length 10 to the power 9, 1 billion.